Hello and welcome to Learn Data. It's great to have you back. On this particular video, we are going to continue to learn about pandas, and we'll specifically talk about interpolation. How we can interpolate or find new values to replace the missing values in a data set. The methods that we are going to look at are listed here. These include time, linear, quadratic, cubic, barycentric, p-chip, anima, spline, and polynomial. We are not going to go through the conceptual details or math behind each of these methods, but what we are going to do in this video is focus on how to implement them, how to write a code to use any of these methods to fit to a data and kind of print or find missing values, that is replace the missing values by these interpolated values that are found by these methods. We'll also look at the limit direction and limit areas parameters that we'll be using with interpolate function. So let's get into Jupyter notebook and start coding. Here I've already created a new notebook and imported three libraries: NumPy, Pandas, and Matplotlib. Today we'll be using it for some plots. For datasets, we have the series A and B. Then we have this data frame dfmn. Then there is this second data frame dfx. There is another data frame dft. I'll try to post these data frames and series in the description of this video, so you don't have to worry about typing the entire data. You can just copy paste it in your notebook. So let's first look at what the data frames look like. So this is our series, which has a bunch of n values that were created on purpose. Then there is this series B, which has floating point numbers and n values. Then for the series dfmn, the series looks like this. For dfx, we have a series that has both original values and the same columns are created here, x and y, where I've deleted some of the values and replaced them with nans. So what we'll do is we'll predict or find the interpolated values here and see how they compare with the actual original values that were present. And finally we have a dft data frame. Again, this one has the x original and y original for comparison, and the difference here is the index here is a time series, so we have dates as indices, and there is a specific method that we'll use for this data frame. So let's get started. First, what we'll look at is the method time, and in this method we are going to use the dft data frame. So let's start with what I'm going to do in this video is create plots, and I think the plots are the best way to convey the interpolation, how it is working. So dft.head, this is the data frame that we have, and now if we simply go ahead and say dft.interpolate, and here if you do not give anything, still here now we have the interpolated values, so all the nans are replaced. Now if we give dft.interpolate and method is equal to time, then again, as we can see here, we get similar values. The default for interpolation is a linear method. Linear method means it tries to fit a straight line between the 2 points between which it has to find the new values. Okay, so if you do not specify any method, it will use a default method. And for time series, this is the method time that takes into account the time series that's in the index to interpolate the values here. Now if we go ahead and plot this, so plt.plot dft dot index, that will be our x-axis, and then dft x underscore origin. So this is the original data that we are plotting first. Marker is equal to O, so we'll draw a circle, and then marker size we'll set it to say 20, and alpha is just to add transparency to the image, so we'll set it at 0.25, and color we'll set it to gray. Okay, so now let's see what the error is. Line 2D property has no okay, so that's my mistake. This is marker. Okay, so this is our raw data that is all present. Now what we have done is we have deleted some of the values in here, so we'll go ahead and plot those. plt.plot dft.index, that's our x-axis, and again now we are plotting the values for dft x. Color, we'll change the color so that we can identify what these dots are, and we'll set a line width to a little thicker line so we can identify it, and plt.show. Alright, so these are the, so here's what we have done. The gray lines that you have that you see in the background, that is the entire data set. Now we have gone ahead and deleted these data points that are in between over here, and what we are going to do now is use the interpolate method time to see if we can interpolate the some of the data points that are missing in between there. So if we go ahead and look at the dft data frame, which is right here, we see that these 4 data points are missing. So we'll try to find those in what we have and see what we get. Before we do that, let me go ahead and rotate the x ticks so that we can read the x-axis. Okay, now it's better. So here we can go ahead and now add the interpolation. plt.plot dft.index, that's our x-axis, then dft x, and here when we are interpolating, the way to interpolate is dot interpolate, and here we are going to give method is equal to time, and then again we can change the marker so that we can easily see which are these interpolated points on the plot, and then we can say the marker size is equal to say 10, and color is equal to, let's give it orange color. Okay, so now as you can see, this is the data set. So the interpolated points are right here in between. As you can see, those are denoted by the plus signs on the orange line. So the actual data points were here, but then the interpolated points are right here, so it's like a linear fit. So that is good to know, that when you are interpolating or finding values that are missing, it may not always be what you want or what the actual data is, but they can be close to what the actual data is. So now let's look at another example. So we'll talk about floating points, floating data, floats in data. Let's do that. And for floats, we created the series B that we have here. Now to interpolate the points in a series that are floats, there is a method that is called values. So if you say b dot interpolate method is equal to values, then the missing values are interpolated or found, So 0 1 and then so 0 0.1 0 0.2 and now we have 0 0.3 that was found, and then 0 0.5 and 0 0.6 that were found as well. So that's just to remember that if there are floating points, the method values can also be used. Now moving on, let's use our other data frame, the other series that we have, which is the series A, and there we'll try to use different types of methods, and there are several of these, so we'll tackle each one by one. Okay, first we'll go ahead and plot, create a scatter plot with the original values. So we have a dot index, the data from the series that we are going to work with is this. It just has 1 2 3 and 5 values, and out of we'll try to plot this series first. So x dot index, a dot index, which is going from 0 to 16, and then we'll plot the values of a and label this as original. Okay, and then we'll set the size of the dots to 400, and we'll set the alpha to 0.5. Now if we go ahead and say plt.show, we can see that this is the plot, that data set that we have, and there are several missing values in here. There are several missing values in these areas as well. So now let's go ahead and try to find the missing values. First we'll use the linear method that is default. So plt.plot a.index, a.interpolate. So we are directly writing it in here. So a.interpolate method is equal to linear, and then we can set the color of this to red. Let's set the marker to the similar the circle that we have, and label this as linear. Now why don't we go ahead and add alpha value so it becomes a little dimmer. Okay, so what the linear method is done as, it has between these 2 points, one is at 2 and other one is at 6, it found these 3 values that were missing, and this is a linear fit, so this line is straight right here. Then between these 2 points there was this point missing, and found this as a value. Similarly these 2 points and these 4 points here. So that's how the linear interpolation method found all the missing values that were in this particular series. Now let's go ahead and use another method here, the pl, and for this is going to be repetitive, so I'm going to copy this and paste, and we can go ahead and change just the method so we can save time. There is another method called quadratic, and we'll change the label here, and color could be changed to blue, and marker could be circle. That's fine. Now as you can see, when we fit a quadratic line, it has a different structure to it, and therefore the points that were found by this method were not the same as the linear method, and we have these points in blue, which are blue dots between these 2 points, and there is one, this point is exactly the similar to the linear method. These points, 2 points are also similar, but then these 4 points and these 3 points are different as compared to linear method in the quadratic method. Now if you look at a cubic, and let's add this maybe sky blue. I'm going to add cubic, And why don't we start seeing the plt.legends, and now we can see the legends. So again the cubic line is different than the quadratic line that we had fit earlier. So that's another difference that we can see. Moving on, let's look at yet another method, which is polynomial. Now while using a polynomial method, we also need to specify the order. So let's try a second degree polynomial, and here we can give this color gray, and it could be still be a circle, and here we can say polynomial. And now the polynomial, as you can see, it is the same as the quadratic that we had, so second degree polynomial, right? Now moving on, let's look at the method spline. So in case of spline, again we need to specify the order, and why don't we give a color? So let's use a yellow color in this case, and let's label this as spline. Now when we run this, so this result is similar to the quadratic or second order polynomial, but as you can see, the yellow line is pretty close, but it's not exactly the same. Next up, let's look at a method that is piecewise polynomial. Piecewise underscore polynomial, and for this we can give another color. So let's give this a color olive. So I'm going to call this PP for now, piecewise polynomial. And as you can see, it is more close to the linear method that we have, and it's overlapping the red data points. Moving on, there's let's look at another method, which is krogh, and let's go ahead and add a new color to this one. Okay, so here we can give it maybe a green color, and let's add a different sign, so maybe a plus sign, and label is that. So now when we run this, okay, so as you can see, this is the new line that is created right up here. So in this particular region, it's pretty close to the cubic feet, but up here that line deviates substantially from the other fits, and it's seen right here for the green line for this particular method. Now after this, let's look at yet another method, which is barycentric, and for this we can go ahead and change the color to maybe orange, and let's change the marker to X, and this we can see again that this is pretty close to what the earlier method was, and it kind of clearly seems to overlap the krogh method in, I hope I pronounced it correctly, that method in this particular data set. Next, let's look at another method called pchip. And for this one, we'll change the color to black, and let's go ahead and change the marker to maybe a star and call this p-chip. And this method, as you can see, is different in the sense that in this part it does not overlap with the linear part, but then in this region it overlaps with the linear or linear method, and here it's overlapping with the quadratic spline or the polynomial method output. So that's the difference between all of these methods. Now there is one final method that I want to show. It's the anima method, and for this let's use yet another color, maybe magenta, and for this we can use a triangle. Okay, so as you can see that this method is again pretty similar to the cubic, quadratic, polynomial, then the barycentric in this region up to here, and here it deviates a little bit, as you can see it's going a little on the upper side of the linear method. Why don't we move this B box to anchor, and we can give it 1 1. Okay, so now we can clearly see where the data points are, and this is the magenta colored line which is for anima method. As you can see, it's different. So this chart is just to show you that it will be a method. What method to use when would be dependent on the type of data set you'll be working with, and we'll look at two more examples to see how these data sets find the missing values. Now the next method, we can use the table that we had. So we had another table, dfmn, this particular table. So let's use that one, and what we are going to do is we will keep everything as is except the values for x and y. So I'm going to change the x and y values here. That is the x value dfmn m, and a dot index is going to be replaced by the first column m of the data frame dfmn. So we'll do that for all these plots that we have, and then for the y-axis we'll use the column n instead of the a that we have written there. Okay, and change that, so that, okay, all right. So as you can see, this method is, so what we are getting here, I think I'm missing something. Let's go back. So dfmn, so this is right. Okay, so the reason why we got a plot like this is because in this particular data frame we have the missing values in the column m as well, so we need to interpolate those values also. So what I'm going to do is copy paste the same method of interpolation for that column as well, and then we should be able to see the result of interpolation for both the columns m and n. So this is for polynomial, then we have the spline, and then we have the piecewise polynomial, and we have this method, and then we have barycentric method, and we have the p-chip, and finally we have the anima method. Okay, so when we run this, now we are able to see what the interpolated data points look like. As you can see on here, this particular method, so these two methods, and this looks like one of them is spline, so we can kind of go ahead and find those. The markers on here are star, x, so this is barycentric, and then we have a plus sign as well, so krogh. So those two methods seem to be trying to interpolate out of the scope of the data set that we had. So if we go ahead and comment these, I'm going to use the 3 quotes right now. Let's see. Okay, yep, so these are the two methods that seem to find these two data points that are way out of the line of the actual original data set. And so again, plotting helps to identify which method could be useful to interpolate the values for a given data set. So I'll always recommend to, as far if possible, fit the data set, fit a method to the data set and see which looks better, and then proceed with the method that you think is actually representative of the data that you are working with. Now moving on from this method, let's look at yet another method. So in these methods we saw that these two methods, the barycentric method is not really working well. However, the linear method is doing pretty good in these particular cases. However, there are instances when the barycentric method would outperform the other methods. So let's look at the data frame dfx, which is this. And for okay, before we move on, I just want to show, I think we had, let's go up in the data set. We have dft. Okay, we saw that okay, we are good. So for dfx we have the original values as well, so we can cross check with the interpolated value as to how far or how close we are to the actual original values. And here now we are going to use the data frame dfx. So I'm going to go ahead and change these values that are here to dfx, and the instead of m, again we have the data frame which has the values original. So if we use the, let's just pull 2 rows instead of all of them. Again, this would be x. Now the original, we are going to use x original. This is going to be an y original. So that will be our base to which we'll compare the interpolated values. So now we'll use the interpolation for the column x, and then we'll use the same method for interpolation for the column y. I'm sure there is a way to replace all these values in the cells at once. I need to find that. Okay, and then we have the value of y that we would need here in place of n. And this is a sinusoidal data set, so you'll see that the plot is going to look different, and this is an awesome plot. So let's print each of these one by one, so we can kind of appreciate the interpolated values by each of these methods and kind of understand how well they do. So this what we see, the blue dots in the background, that's our original data. Okay, now we can also go ahead and print or put there the x and y values, which are the missing values, and we'll give that a color. So let's do this. Remove, sorry, face color is equal to none. What that will do is we are removing these blue circles, and we'll just keep the outline there, and color is equal to gray, and this is will keep as 400. Okay, so when we run this, so here's what we have. These empty circles, that's our actual original data set, and the blue circles, they show us what values we have to start with the interpolation. Okay, all the values in between, which we see as empty circles, those are not seen by the interpolator. So the interpolation is working with only these blue dots, which are labeled here as missing. That's the series. Now if we fit a linear method to this missing value data set, then we can see the red dots that are found by that method, and as expected, the linear method would fit a straight line between the two endpoints. So from this point to this point, it fit a straight line. Then again from this point to this point, it fit a straight line, and then predicted the equidistant data points that for the missing values. So that's the best the linear method was able to do. Now let's use another method, which is quadratic method, and as we can see, quadratic method is doing pretty good as compared to the linear method, and it was able to find almost all the data points in the first half. Only in this last part is not able to interpolate the values quite well, but still it's close to the actual original values. Now if we use a cubic method, it finds the values similar to what we had for the quadratic, and in this particular region where the x-axis is at 8, the curve doesn't go as high above as 1 where the original values are. It stays below and it comes down right here. Next, let's look at the polynomial of order 2. It will be similar to quadratic. And now the spline. Now if we look at the spline, we can see that it is nowhere close to the earlier methods, and it's out of sync in this region around 2 and around 5, and in this region between maybe 7 and 9. So definitely for this data set, spline of degree order 2 may not be a good idea. So if we change this to degree or order 4, it's still not working as well. Now if you try the piecewise polynomial, it's similar to the linear method prediction that we saw, and it kind of overlaps all those values here and also here. Moving on, let's use the method krogh, and this method is doing pretty good. As you can see, it was able to go up to 1 at the x-axis value of 8, and it was able to find all these missing values. Just based on these 5 missing values, it was able to go up here and find these, and it also correctly found all the missing values down here between 4 and 6. So that's pretty awesome. Now if we look at the barycentric method, and we can see that that method as well is working as good as the earlier method. So I'm going to comment out the earlier method so that we can see that plot clearly. and we can see that this method also correctly is able to interpolate or find the missing values in almost entire plot here. So that's pretty impressive. Now let's look at the p-chip method, and this method which is denoted here by star does not do as well. As you can see, this it between 6 and 10, the line is right here just above the linear method. Also between 4 and 6, it's right here, and similarly here. So maybe p-chip method is not good to work with for this type of data set. Now moving on, let's look at the anima method, and again this method is better than the p-chip method for this data set. However, still it's not as good as the barycentric or the krogh method that we saw there. So if we now go ahead and plot all these methods together, this is the final plot we get, and this is kind of the gist or the summary of the entire interpolation method. So key things to remember: first is try to fit the methods to the dataset and see if it's able to interpolate the known values correctly, or if they are even close. So I'll just pick the known dataset first, delete some of the values, try to fit these methods, see which one fits well, and then use that method which fits well to the rest of the dataset, assuming that the distribution stays the same in the rest of the dataset. That's the assumption there. Okay. And if you have any questions as to how these methods actually work, what goes on in the background, please let me know in the comments below. I'll try to make another video for that if there is a lot of interest in knowing the background, like the maths behind it. Now finally, before we conclude this video, let's look at limits when using interpolation. Okay, let's look at the series A that we had earlier. So this is the series. Now if we type a dot interpolate, we know that we are going to get a linear fit between the data points, and as you can see, all these data points between here are now 36, and then between 6 and 36 we have these two data points that are equally spaced, and similarly we have these data points up here, and the initial first two values are still n because there is no data point before the zero index that could have been used along with this minus 100 to find those values, so they stay as nans. Now as we saw, I think we saw in the previous video, but we'll talk about it again here. So if we limit, similar to padding, if we limit the interpolation to 1, then we'll replace the missing value by a interpolated value in only one row subsequent to the row which has a value. So if we type limit is equal to 1, then after this 36 there is just one value of 36, and similarly after this 6 we just have this one value of 16 that was put in the data set. If we go ahead and change this to 2, then the limit becomes 2 and 2 values are found, the others remain as nans. Now in addition to limit, there is another method where we can change the direction. So if we type a dot interpolate limit is equal to 1 and limit underscore direction is equal to backward. So this is similar to the backfill that we have seen in the previous video. If you do that, then what we are actually doing is we if we pull the A again, as you can see, there are two missing values here, two NaNs before minus 100. Since we had backward limit direction, the method put a minus 100 in the empty space above the minus 100, so which is this one. Similarly, there are missing values above 4. There are 3 missing values, and one value was put in there, which is minus 22 as NaNs. Now the reason why this stays as 100 and this was actually calculated was because here this particular 4 data point has the other end of it, so it's like a bridge. One end of the bridge has 4 and the other has minus 100, so in between it is able to find the equidistant values, and it puts only one value because we said limit is equal to 1. Similar to backward, there's also a way we can put both, and if you put both, in that case for this particular example, if you say minus 100, one value was put in the backward direction, which was at index 1, other value was put at index 3, which is forward. So both means it will put on either side of the number which has a missing value. Now probably guessed, is there a forward method? Yes, there is. Forward direction. And if you put forward, it's exactly opposite of backward. So nothing is put above 100, so we just have this minus 74 as a value put after 100, and that's for the forward limit direction. Now beyond this, there are other interesting things we can change during interpolate. One is we can limit the area. For example, if we want to interpolate only inside these areas where there are bounding values, so this value is the bounding value here, this value is the bounding value here, there is no bounding value here because on the top. So can we do that? And let's see how we can. So if you type a.interpolate, again we can limit the direction to both, and now what we can do is we can limit the area. So if you type limit underscore area is equal to inside, and let's say limit is equal to 1, now what we get is the values inside of the known values are filled. All outside values are kept as NaNs. As you can see, the values at index 0 and 1, they stay as is. However, all other values are full. Now the reason why the values at index 4 and index 13, 14 are NaN is that's because we have put a limit of 1. If we change this limit, or if we remove the limit, then that won't be the case. So if you say limit 10, then all those values are filled. Okay. Similar to inside, and you guessed it right, there is also outside. So if you say outside, then all the values, where did it go? Okay. So when we specify outside, all the values outside the known values are interpolated, and the values inside those known values are kept as is. So here the outside values were at index 0 and 1, those were changed, but all the values between the index 2 and index 16 remain as is, and the NaNs are not changed at all. Okay. So that was the parameter. That were the parameters that could be changed for the interpolate method. I hope in this video you learned several methods that could be used to interpolate data, especially in this figure. So you have now an idea of what methods are available in your toolkit to find the missing values, to perform any type of analysis, and what are the parameters within the interpolation method itself that could be changed to tune your process or steps for finding the missing values. And if you, I'd really like to know how you found this particular video. If you have any comments or suggestions, please post them in the comment section below. I will see you all in the next video. Please like, share and subscribe. Thank you.